And finally, we've reached the interesting part, the discussion of shared memory. So shared memory is different. It has block scope, which means that it's shared only within a particular thread block, and it's not shared between blocks, which certainly makes using shared memory a bit of a pain because you can't just access it from everywhere. Now, shared memory has kernel lifetime, meaning that you have to basically declare it within the kernel function body, and it goes away after the kernel has executed. But the great thing about shared memory is that it's very fast, and this is why there is motivation to use it, even though there is additional complexity in that. So instead of doing this in a theoretical way, let's actually take a look at how shared memory is used. And we're going to jump back to our reduce example. You remember the reduction where we did a reduce sum, and we're going to rewrite it using support for many thread blocks and shared memory as well. Okay, so here we are back in our reduce example, and I just want to point out what's actually happening when we perform a sum in a single block. And we're going to stick with this idea of using just one block because with many blocks, essentially you end up doing two reductions, sort of a global reduction on the blocks and then a second reduction. So I'm going to keep things simple, so we're going to stick with this sum simple block example. Now, what's happening here is that we've got an array of values D, and that array of values keeps being reused. So essentially, as we reduce from n over 2 elements to n over 4 elements and so on down to the last element, we keep reusing device memory. So we keep reusing global memory, which isn't efficient. So the alternative here is to start using that shared memory that we talked about, and also figure out the third kernel parameter that I promised to tell you about. So how would this actually look? Well, the idea is that we're duplicating the array D. So whatever we do, we need shared memory to take up as many bytes as the D array would take. And the way you specify it is you specify it as the third parameter to the sum single block method. So if I'm going to, let me just duplicate this entirely, because we're going to make a couple of changes here. So I'm going to duplicate this block, and then I'm going to say, well, let's have this as sum simple block 2, and change the call here. Okay, so we know we need shared memory, and we need as much shared memory as there is elements times their size. So essentially we take that size value because we're going to replicate the array entirely. So I'm going to put size in here. Okay, so now that we've specified how much shared memory we need, how do we actually get it? That's the next problem. And in actual fact, it's not a very difficult declaration. So essentially we say that we have an externally defined specification for a shared array. Let's call it D copy. So it's going to be a copy of the elements in D. And now that we've got this this data structure, and we assume that it's initialized to the right size, what we do is we copy from D to D copy. And keep in mind that the number of threads is actually half the number of elements, which presents a bit of a problem because when we have a TID, it's actually at a position n over 2. So to copy something to dcopy, we essentially say that dcopy at TID times 2 equals D at TID times 2. And then let's just duplicate this and shift it by 1. This is a natural consequence of the way that we've done things in our attempt to save on the number of threads that we're using. So apart from this, not much needs to change. Obviously, instead of using D in all the calculations, we now use that faster shared memory. So D copy here and D copy here as well. And then when it's all said and done, all we want to do is to save the first element of D copy in the first element of D. And we can say that if, let's say, if the thread ID is equal to 0, so we only need to do it once. So if thread ID is equal to 0, then we say D at 0 equals D copy at 0. So let's try running it and see if this works. All right, so it's saying that the sum from 1 to 32, I think, is equal to 5 to 8, which happens to be the correct result.